on the previous lectures. So that while my intention was to go very high, I go lower and lower. So today I will start by clarifying what I said last time. So this is then lecture 01. So again, the experts will think that this is boring, but look at this as a pedagogical challenge to lower this down to the algebra case. Because I told you about schemes and functor of schemes. And it's very good that you know that there is something like a scheme, so that we have some geometry. But that geometry is the geometry of algebras. And you are experts in cluster algebra, so you rather would like to look at an algebra. So a scheme is just the geometry of an algebra. So now I start with an example. And it is an important example of functors. So let L be a k-algebra. So L is an element in algebras over K. So you are familiar with that? It's a k-algebra, it's an easy object. So look at the following functor. That is morphisms from L, and that is the variable, going from algebras over K and into sets. So what is this functor doing? Well, it takes an algebra S and sends it to the set, which is, okay, I can equally use hom, because the morphisms are homomorphisms of algebras. So to the morphisms from L into S, which, by the definition of categories, should be a set. So think a bit, why should this be a set? If this went into some other category, then we call this an enhanced functor. And that is the basis for the derived functors and such things, derived categories. But for now, it's just a set. So what is this functor doing? Well, it is covariant, because given a morphism, a homomorphism from S to R, then this is of course sent to homomorphisms from L to R. And then we have a morphism this way. And what does this do? Well, it takes a morphisms from L to S, call it phi. And then I have a morphism from S to R. That was this one. And we take the composition. And then I get this usually denoted phi star down, which is here. So this is how this functor works. Should be possible to understand. So what is so important with exactly this functor? Well, the morphisms, which is the same as the homomorphisms in this case, from L into K, which is the base field. This is then the set of all homomorphisms from L into K. But then the kernel of such a morphism is always a maximal ideal. So this is the set of maximal ideals of L. And that was the geometric points in the spectrum of L. So in the geometry of the algebra, these are the closed points. So that's why this functor is called, or this functor is called a functor of points. Okay, the other important thing, so this is the first important thing, the other important thing is that assume that there exists another functor of points, which is equivalent. So assume that the morphisms of L prime is equivalent with the morphisms of L. If there is an equivalence between two such functors of points. Well, then we have two things. Morphisms from L to L prime. I put in L prime here. Is isomorphic to, as a set then, so it's in fact a bijective correspondence with the morphisms from L prime to L prime. Okay, I put in L prime there, and I get L prime there. So I turn it around. That was not very good, but okay. So there exists a row here mapping to the identity here. Also, I would have a morphism from L prime to L. And this would be isomorphic to the morphisms from L prime to L prime. No? From L to L, of course. And I wanted to say L prime into L prime L, like that. It's crazy. I did this just this morning, and this never turns up right. So there exists the row prime up here, mapping to the identity here. And it should be not like this, but it should be, look at my diagram, L prime to L to LL, like that one, of course. Mapping to the identity up here. Yes, that was the equivalence. So this implies, in fact, that there exists L to L prime by row, and then down by row prime to L, composing with the identity. And also the other way around. So this says that every other such point functor, or with algebra, will factor through L prime. And in fact, it says that L is unique. If there is another algebra, it has to be the same one. So that's why it is called a moduli, or in fact a local moduli, because the spectrum is local. So this was just to tell the importance of these representable functors, which even the master students should be able to follow. So the points are the maximal ideals. So now let's look at the moduli functors from an algebraic side. So I call this affine moduli. So now we look at the functor. Now it's a family of A modules parameterized by, that is my goal. So I look for a functor from algebras over K into sets. Exactly as this functor of point was. And I let f of r take a k-algebra, then f of r is equal to the set of r tensor k A modules. This looks, of course, exactly like yesterday, but now it's easier. It's no schemes here, it's just algebras. S tensor, R tensor K A modules. And they are named MR because they live over R. So how is the, if I have given the morphism from R to S, how is this functor then given? Well, let's write up what it is. This should be S tensor Ka modules, MS, and then I should have a mapping here. And this takes the module, or one module, MR, living up there, and sends it down to S tensor over R, MR, which is also, then I can take, it is an S tensor over R, and MR was an R tensor over Ka, which is S tensor over Ka module. Okay. So I have a family of modules. This is called the family of modules parameterized by R. It is just an R tensor over Ka module. And I map it down by tensorizing over R by S. Then I have the functor. Okay. Notice that f of spec k is just A modules M. If I put in K here, sorry, it's only K. If I put in the field, then I get just A modules. That's why these A modules are parameterized over R. Okay, so now M, here comes up this moduli space again, but now I let it just be an algebra. Or I really let it be spec L. So let it be the spectrum for some L. And then this is called a moduli, and now it is a moduli space. It's even a fine moduli space. This is equivalent, by definition, that F is isomorphic to, and now I do this algebraically, is isomorphic to the morphisms of points from L and in. So this is the affine definition of moduli. M is called the moduli scheme for A modules if this parameterizing A modules F is isomorphic to the algebra functor. Yes, and we know that when we put in K, we get all the maximal ideals. We go all the maximal ideals here. And now I define the fiber functor, which I did last time, but this time algebraically. Definition. fix a module M, then the fiber functor of F, I can equally define it not only from algebras, I defined it from the pro category of algebras. This just said that it can be extended to this category by taking limits. So if you don't like the hat, just remove it. And if you don't like the pro category, remove the hat. Should go into sets. And then the fiber functor is given as, no, this should be a functor. And Fm of S, now I defined it without a hat, because then we just have to take the limit. It is all the modules Ms in F of S, such that F of I, to use the precise notation, and I will tell what I is afterwards, of Ms is isomorphic to M. And then we have S to S divided out by M by I, and M corresponds to M, which is equal to L divided out by the maximal ideal, which is the fixed module. Then we get a fiber functor. Let's just write this up to spec L. Yes? Here, S. It is from the category L hat into sets. And L hat, it's the limits over n of Sn, where Sn is in L. And L is all those which was K into S down to K, the identity, and local Artinian. So, for some n. So the point is that I can define this one only on L, and then I can take the limits, because this is the limits of Sn. So I just take the limit of the functor. This is the classical article of Michael Artin, who gives properties for these limits to existence, such things. So I just shuffle that under the carpet, and we assume it exists, and it's okay. For A modules, it's okay. For any Grothendieck category, in fact. So then I have the fiber functor, no defined algebraically. And when I restrict this Ms, doing this one, I then have Fm. No, I have f of S into f of this, which is equal to K. And then I take those that maps to M. And I get the fiber functor, in fact. Okay? And the goal of deformation theory originally was to find the I need to say something more first. Oop. But that fits perfectly under this heading. Assume M is equal to spec L is moduli. Then in fact, F M is isomorphic. Okay, then then F is isomorphic to more L bar. That was being a fine moduli. And this implies that F M with a hat is isomorphic to the homomorphisms or morphisms. I'm not consequent here at all. Isomorphic to the morphism from L localized in M. I should say M, the maximal ideal, corresponding to M. Completed, just localized in M, completed, and bar. So then this L localized in M with a hat, this is in fact a local moduli. At least locally, it is a moduli. And then the goal is approximate L M hat. If somebody say that we are studying the moduli of, for instance, curves of genus G, then we know there exists a moduli space. Then it's very interesting to find the local rings on this scheme, even if it is completed, because then I can say something about the dimension, the regularity, the type of singularity, and I think that was the basis for this theory. Classify the singularities of a moduli scheme, classically in algebraic geometry. And I think that was the reason for the people in Trondheim working on algebra representation theory, cluster algebras, was in big conflict with the people in Oslo doing algebraic geometry, because they were interested in different things, and then they liked to quarrel at the old times. But no, I feel that we are closing much more up to the representation theory than we did before. So this was exercise 01. Well, it's perfect. So I think you would be able to follow the rest. But of course it wouldn't be this easy maybe. I'm just scaring you so that you are concentrating. This is a module. It's an A module. And it's even an A module isomorphic to K. Yes, okay. So the module M is not equal to this one. It corresponds to this point. You're right. Because L has maximal ideals in correspondence with the modules A modules M. So that's why. Very good, very good. Okay, just ask. It's no problem. Because now I could start by defining the deformation functor, which is a functor which goes from L hat to sets, and I can construct local formal moduli who would be an approximation. But because there exists, after a while, non-commutative deformation theory, and this includes the commutative, I can just start there. So I just have to define a new category L hat. So I start with Quiver algebras with relations. And the point is that I'm not interested in Quiver algebras originally. I just wanted some non-commutative polynomial algebras, in fact. But people have problems to understand what I mean, or what Arnfinn Laudal means. That's why. So, commutative algebra. What are we really studying? We always start with a finitely presented, finitely generated k-algebra. So what we really do is starting with A is equal to k, x1 up to xd. That's in the basic courses. If this should be independent of the coordinates, then we call it sim k of v, when v is a d-dimensional vector space. We look at the symmetric algebra over k. So this is just to say that you choose the coordinates. Nothing more. And these are the basic objects in ordinary k-algebra studies. So now I do this in the non-commutative case. Non-commutative algebra. So I can consider a k to the art module, k to the art, r copies of k, just the Cartesian product. And I would like a k to the art module, v, which is equal to vij. Okay? 1 less than I and j less than equal to k? No. R. We look at R times R matrices. And I can let each of these has dimension dij, is dimension. Because this is a matrix. It is a vector space, V11, with this dimension D11, V12, D12, V1R, D1R, VR1, DR1, VR2, DR2, we choose vector spaces, Vij, choose all these vector spaces, only vector spaces of respective dimension. No, first you choose all these Vij, then you define V as this one. So V is defined by this one. Well, you can choose your favorite vector spaces. R by R matrix. Well, k to the art, k, 0, 0, 0, k. So just k on the diagonal. And then you just multiply it. Yes, so it's a diagonal matrix, R times R. And you multiply it with this V11, V12, and you can do that for both sides. It's perfectly okay. So it's a k to the art module. And k to the art is a k-algebra. It is also a k to the art algebra. Except that k to the art is no field, but maybe a division ring. I don't know, but at least it is a k-algebra. So the point is that, okay, I have the dimension. And I define now just to keep notation. So when we are doing this one, when I tell this A, there is no reason why we should have these x's there. If you know it was d of them, that would suffice. So in the notation of this could be, if it was up to me, I would just call this kd. If it was up to me. So this is just to say that it will be a lot of variables to put in this notation. So it is much more easy to say that I use the notation f of, and I use angles because this should be non-commutative. And I let the variables be numbered by the dij's. That was the dimension of these vi's. So this is just the notation. I define this one as the tensor algebra as k to the art module of V, which is a matrix algebra. And the only reason is that I would be able you to understand what this is equally like. So this is then, in this notation, k in angles, because it is non-commutative, T1, 1, and I should have D1, one of them. So I just put a bar under. So you understand that this is bar. Note that Tij bar means Tij1, Tij2, and on up to Tij, Dij. So Tij is a variable. I just explained what T11 with a bar under means. This means T111, T112, up to T11D. Exactly as I usually use the notation Kx bar to save chalk or ink or paper. So then I have all these variables and I have k in front of them. This is the ordinary non-commutative free k-algebras in these variables. Here, I only get the vector space generated by T1, 2. Again, there is D1, 2 of them. And so on to the last one, which is T bar 1R. Down here, I get T12 bar. No K. This is just a vector space generated by this. But on the diagonal, I get a K all the time, because I multiply in this K. this k will be mapped to the diagonal when I'm mapping this in as k to the algebras. So I have k T21 bar up to T2R bar. And of course, continuing this way, I end up with TR1 bar I have TR2 bar, and I end with K T R bar. This is a matrix algebra, and these are the generators. If there was to one term, yes, it just means the vector space generated by. It's not an algebra. But of course, now I take the algebra, it is in fact the algebra over this one. It is the symmetric algebra, tensor algebra over this one. It is not the symmetric algebra because it's not commutative, so it's the tensor algebra. This just means that it is the algebra generated by this one. So inside here, we can have, for instance, T11 times T12. This is an element lying down in T12. Because it really means the matrix with T11 there and T12 there. And also we have to define that Tij times Tkl is 0 when k is different from L. So we multiply them exactly as matrix elements. And this was impossible, for instance, for Idun Reiten to understand. Completely impossible. Because they doesn't look like this. So they wonder where this was. And then the final solution to get Sverre Smalø and Idun Reiten to understand it, those are the most famous. It's actually Reiten as in Auslander Reiten. And the only way to get him to understand it was to say that this is the tensor algebra, and this is in fact the Quiver algebra. And of course, there are no reasons not to claim some relations. So when we have something like this, if we have P is equal to some F, this indicates that it is free, but it is not free because it has the relations that something are 0. So it's really not free, not a free object. So we call this one F, and I use this bracket and the matrix Dij for notation, and divide out by an ideal, a two-sided ideal it has to be. Then I call this a Quiver algebra with relations. So QR is equal to a Quiver algebra with relations. And of course, it's very hard to work with these big things. Yes? This is a non-commutative analog of the polynomial algebra. I'm taking the quotient by an ideal, and then I also get some relations in the non-commutative. So it would be absolutely the non-commutative analog of an affine algebra. Yes. But to define the affine space is one more step to go, namely defining the localizations in simple points. In your case, on the diagonal. Yes? I can indeed. And, and I will. So example, it just would be something from my arsenal of points. So I look at K, T1, okay, T111, T112. Now I use square brackets because I want it to be commutative. Just for the case of the example. No reason to do it, but I do it now so you can see some geometry. I put in T1, 2 up here. There's only one of them, so I don't put in a 1. I could have used that, but I don't. Strange measure. And I just let this be 0. And I take K, T22 here. And when there is only one variable, this will always be commutative. So there, you can't have a non-commutative algebra in one variable. So, like this one. Excuse me? 1, 1 is of dimension 2. And I divide out by the ideal. T22 times T22. And for instance, okay, this one, minus T11 times T111. No, that was not there. I thought the other way. T11 times 1 times T12 times T22. This is possible. So then this is just T22 squared. So I take a fat point on this line and identify this via T12 to a point up here in T11, if you want to see the geometry. Because this is affine space, and this is A1. This is a line. So you can play with geometry, and that's the point of it. But then you have some problems with the tangent directions. And that's the point of this non-commutative schemes. That is that this is a tangent directions, in fact. And the whole philosophy, if there is any philosophy in this game, it is that we don't look at these variables as coordinates. We don't look at the arrows between nodes as homomorphisms. We look at those as tangent directions. And those also as tangent directions, not homomorphisms. And this is a new philosophy. For those who are physicists, when you observe things, you don't observe the point. You observe the change in the points. So you observe the derivatives, not the point. You observe the tangent directions. So, this is an example. If you understood it, it's great. But do you have problems with where this lives? Yes, if you absolutely want a quiver, you have two nodes, and you have the loop, because E1 is included. E11, E12, You have a tangent direction from 1 to 2, T1, 2. And that's about it, yes? Sorry, you have two, two vertices here. Two loops. Thank you. That's not how you write it, but it's... Okay? So you can find a quiver if you want to. But of course, I really allow loops, and there is no reason for not having cycles, 2 cycles. So that makes it quite different from a cluster algebra. So again, usually I get really stressed when I don't move away. But I see now that the professionals are falling asleep, and that's okay. So then you master students can follow. And when you know the basics, you can do the rest yourselves. Now I want to tell you what the ring of dual numbers is. Ring of dual numbers. Okay. Let's start in the commutative case again, so you see where this comes from. So, commutative case. Why are we interested in the ring of dual numbers? Well, if x is equal to spec A, what is the tangent space in a closed point? Well, for those of you who knows differential geometry, the tangent space is, well, what is it? It's a vector bundle with some sections and some. But what it really is, it is the space spanned by the tangent direction. What is the tangent direction? Well, it is a basis for the derivations. Every derivation can be written as a sum of derivations along a basis. For instance, in Rn, you can derive along x1, x2, up to xn for a chosen basis. So the tangent space of spec A in a closed point M. So the tangent space of A in a closed point M, that's our closed point M, that's a maximal ideal. Then this is equal to the derivations of A into K. And the derivation is just a derivation. Something in here is a derivation if delta of, okay, if d of AB is equal to A dB plus dA times B. And now, if A is non-commutative, this would be important. When it is commutative, it's of course not. This is the derivations, and then this is equal to the homomorphisms over K from A to, I write kx divided out by x squared. Is that true? Of course it is, because when you double it, it will vanish. So this is the same, this is the homomorphisms here. And it is in fact determined by by m over m squared dual. Because A is, if you look at it as a vector space, k plus m. So the derivations, the k homomorphisms, is determined by their value on m. So this is in fact equal to the dual space. That's why we define the tangent space in a maximal ideal at the dual of m over m squared. So the usual notation is then kx over x squared is equal to k epsilon. And that's the ring of dual numbers in the commutative case. And this epsilon, this is the usual very small epsilon. And so this is called the infinitesimal ring as well. And when we are speaking about infinitesimal deformations after a while, this is deformations over this ring. So, now we do this non-commutative. Then it's easily, I just generalize. E is the ring of the non-commutative ring of dual numbers. It should be the same algebra, the tensor algebra over V, as exactly as before, divided out by the ideal generated by all the Tij's squared. Or maybe I should take the square there. Because there's no reason to square T1, 2. It would automatically be 0. So whenever I have some t multiplied with another t, it should vanish in this algebra. So that is E is equal to this horrible algebra, k T11, T1R to TR1, TRR, and divided out by this Tij squared. The ideal generated by all the t's and then squared. So everything that is squared vanish, and we have finite dimensional vector space. And we should use the bars because it doesn't necessarily have dimension r squared plus r, because we have r on the diagonal also. Okay, so maybe you have enough feeling with these things. Oops. So this indicates that I'm in lecture 1. I'm on page 12 of 37 in lecture 1 in the notes. So now I want to define the category L. But this time in the non-commutative setting. So the category of R-pointed Artinian k-algebras. I think now we are in business. This category L, the algebras in L, they had one maximal ideal because they were local Artinian k-algebras. Now I want them to have R maximal ideals. But maximal ideal in a non-commutative ring, that's a bit tricky. So I wanted to have R simple representations, which is just a translation of maximal ideal. So, because you do representation theory, I know maybe you know what a simple representation is. If not, I can explain when we come to that. But first, the category of these algebras. Objects. I need to say what are the objects in my category. And they are diagrams, exactly as before, but this time k to the rth maps into S by some, maybe iota. And then a surjection down to k to the rth, and such that this composition is the identity. And furthermore, okay. Should I say this? Okay. S should be finitely generated. With, and there should be Artinian. So I claim that the radical I to the nth of S, which we first, this is a bit of a circle definition because it's not Artinian before I claim this one, and this is not a radical before it is Artinian, or semi-simple. So there are some circles there, but doesn't matter. So this is the kernel to the nth of this row. So I define the radical as the kernel of this row, and then if the radical is 0, then it is in fact a radical. With this radical equal to 0 for some n greater than 0. So what are the morphisms? Due to Klaus Altmann, a good lecture is on blackboard with at least 2 colors. So a morphism is a morphism that commutes in the diagram, of course. Oops. So I've used 2 colors. Okay, looks very like this other definition of L, but this time it is R pointed. Think of this R as the R points. No, did I mean really finitely generated as k-algebra? As k-algebra. I mean, you have k to the rth into S, so you also have k into S, mapping k onto the diagonal. And then you get, so this is a k-algebra, and it can be finitely generated. Because this is 0 for some n, it's truly finite dimensional, yes. This will be finite dimensional. And thereby, they have a finite number of simple modules. And thereby, this is in fact a radical. Because this is 0. So that's the circle I mentioned. So. Well, the point is that what I'm saying is that I'm just considering such algebras. Such algebras as this, where I increase this 2 to the n. So all these are really the basic objects of my algebras, of the category. Looks like this one with this one equal to n. And then, as before, I'm going to the pro category. I take the limit. And then they are no longer finite dimensional. So that's how far away they are from being finite dimensional. So when I'm constructing the pro-representing hulls, when we come to that, there will be limits of these finite dimensional algebras. So that's how far they are from being finite dimensional. So how far is the number from infinite? It's a hard question. Okay, but we can look at these algebras. This is in fact a lemma. What kind of algebras do we have? So let S be in AR. What is AR? I should have said that is the category of local Artinian k-algebras, AR. This category is AR. So let S be, I skipped the ob. Just let S be an object in AR and put Sij equal to EI Sej. Where EI is then, what is that? It's the one with 1 on the II entry. So it's iota of EI. Here is iota. And of course, this is k to the r, so I have EI, and I just embed this in on the ith place on the diagonal. This one. Then S, for any S we are looking at, this is Sij as matrix algebra. Okay? Maybe it's nothing to prove. I mean, send S to EI, also little s, to EI Sej. But I'm trying to write a small s. It is illustrating a small s. And then I have an inverse, which then is small Sij. And the inverse, of course, sends all this Si back to, it has to be the sum then of all the Sij. And this is equal. This is a matrix algebra. If you want, of course it is over k, but it's also over k to the art. So it is a k to the art algebra. K to the art algebra, yes. Yes, there are R times R elements. No. Each element is just defined as this K module, which will be a K algebra on the diagonal, and just a K module or K vector space on the other entries. If you did this with this one, this would be S11. This would be S12. And this would be S22. So it's just to be formal. It's a bit crazy. When I teach my students, usually I'm afraid that some of them don't understand it, so they will fail for the exam. And when I'm teaching my colleagues, I'm afraid that everyone should understand it, because then it means that I'm too slow. So I know it is not that way, so just do it. Now we come to the non-commutative deformation theory, or the non-commutative deformation functor. So, non-commutative deformation theory. And then you could object and say, shouldn't we know about deformation theory before you do non-commutative deformation theory? But recall that the non-commutative ring, due to Rothman, I think it was, is a not necessarily non-commutative ring. So it includes the commutative rings. So, I use script M now. Let this be a set of R A modules. Set of R A modules. A associative with units. And also, it's a k-algebra. And it's most easy to assume that it is algebraically closed. So, I just say k is equal to k bar. K is equal to its own closure, algebraic closure. So k is C, in fact. Doesn't matter at this point. It will matter later. Okay, so this is the setup. I don't have one A module. I have a set of R modules. Here is where relativity comes in. So now I define the deformation functor, def. Okay, one more, and one more shorthand. I put M equal to the sum of these modules. This is M1 plus M2 plus MR. R. Just to get a bit more easy notation. So then I define the deformation functor, def of M, which is now the sum of these modules. I could have used this script M also. Sometimes I do, I suspect. Def M from the category AR, R points. Each point was supposed to correspond to MR. That's why I use AR. Into, well, it has to be sets, simple and easy, sets. The category sets. And it's given by the following. Okay, so it will look like the other one. Def M of S. So now S is the k-to-the-r algebra in the category AR. This says I have 5 minutes left. That's perfect. Def MS is the set of, exactly as before, S tensor K A modules Well, I have to decide something here. For the computations, it is most easy to have right A modules. No, A is not necessarily commutative. So then I choose right A modules. Why? Isn't it more easy with left modules? That's true, but when I'm computing in complexes and multiplying matrices, it's more easy with left modules, because we choose to combine morphisms this way. So that's why. I choose right A modules. So these modules are named MS, and I said exactly as before, and you don't know what was before, but it is as in the family functor and the fiber functor. That was the exactly like. But I claim that MS should be S flat. And I claim that K to the art tensor over S by MS should be isomorphic to M, which is the sum of those modules. And of course, I divide out by the equivalences, the isomorphic modules. But that won't bother us much. So, of course, I say that two elements up here, two modules MS and MS prime, are isomorphic. Also, tilde, that says that MS is equivalent with MS prime if there is an isomorphism which commutes with the morphisms to M by tensoring over K over S by K to the art. So let me use the 2 last minutes to say that MS is an S tensor over K A module. And this is always very scary. Have I chosen the right? Shouldn't it be K to the art? Or always a bit shaky. So we will see. Then I get K to the art tensor over S by MS is an K to the art tensor over K by tensor over S by S tensor K A module. Okay? Because MS, that was an S tensor K A module. So then this one times MS is this module. So I can remove this one. That is an K to the art tensor K A module. That is an A to the art module. Then that's great, because M was this sum, which is an A to the art module. So this says that each of these points should correspond to MR. We now tensor it down. And then you can imagine what the commutative deformation functor is. That's the one with only one module, going from L. So this is included. Okay? So then you also see that this is in fact the fiber functor. This deformation functor is the fiber functor. We are looking for a pro-representing object of this deformation functor. That's the goal. And then it turns out that this in fact represents the local rings of some non-existing non-commutative scheme. And I will use these pro-representing hulls to define the local rings. And then define a local scheme and give a non-commutative geometry. So that will follow. Okay. This flatness condition, first of all, is what is replacing continuity in the differential geometry. If you should have any hope to find a pro-representing hull, we need it to be flat. And next time, you will see that the flatness implies that in fact it looks like MS as an A module. It will not, no, as an S module. It will be isomorphic to S tensor over K A. Sorry, M. Where this is the sum. Even K to the R of M. So that makes it possible to make the liftings. As an S module, it is exactly the same, but the A module structure is transferred into M. So, but the basic is that if we should be able to find the pro-representing hull, then it must be flat. Otherwise, there exists no pro-representing hull. MS is S flat. So it's in the definition. Yes? Yes? We really don't know that. But when I construct these modules, starting with this one, this has exactly R simple modules. Because it's Artinian, makes it semi-simple, and then the diagonal contains all the one-dimensional modules. So in this case, when we divide out by this one, we are sure it has exactly R dimensional modules. Yes, it does. Yes, it does. But that's not why we chose it. We chose the R. We take a finite set of modules, that's the point. So I can only localize, when I go further, in a finite set of points. But that's much better than localizing in one point. Because then I can take the limit of all the finite local rings and make it in fact the global functions. You will see. It works nice.